Secant.mp4. So we're looking at the the tangent secant combination. The power of the tangent is m, the power of the secant is n. So this is what we are working on. Once again, we have two strategies. The first one, and you can guess what would be the first strategy in my little introduction. We know that the derivative of the tangent is secant squared. So if we have even power of the secant, then we can factor out the secant squared. Okay, so n, the power of the secant, will be 2k. We need to have at least secant squared. So k going to start with 2. Okay, we can start with 1. For some reason, my note I have k has to be greater than or equal to. Why do we need another secant? The reality is we don't. So let's start with 1. Okay, like so. But I have differently in my note, and I wonder. I have 1 and I change it to 2. So I need to see why. But the goal is to factor the secant squared, and the idea is to get secant squared d theta, and we know that the antiderivative of the secant squared is the tangent. So we need to express something in terms of the tangent now. And we have another formula. Let's recall also.
Secant to the n theta in that.
I'm sorry?
You mean factor secant to the n theta to get secant squared theta d theta?
No, just the secant squared. We want this at the end of the integral. The reason is we're going to use substitution. We're going to say u equal the tangent and du equals secant squared d theta. That's why. Let's also, we're going to use another of the 3 Pythagorean identities. In this case, we're going to use, if we have the tangent, if we have the secant squared, we're going to use secant squared equals 1 plus tangent squared. Remember this identity. So now let's go with our integral. The integral of tangent theta to the n power secant to the n power d theta. We're going to write it as nothing happened to the tangent, but the secant, I know that I want to have, I replace the secant, the n with 2k, like so, right? But remember, I want to borrow secant squared. So what I'll do, I'll write it as secant let's write first secant squared theta raised to the power of k, like so. Now I want to extract from here secant squared. So instead of secant squared to the power of k, I'll have secant squared to the power of k minus 1. Right? So it means that now we have secant squared available to me. Last thing I want to do is to go ahead and replace right there the secant squared with the 1 plus tangent squared. So now I have for some reason I have more steps than I intended to have. So here I have 1 plus tangent squared theta raised to the power of k minus 1, right? And then I have the secant squared theta d theta. And now we'll do the substitution. U will be tangent theta, and therefore du equals secant squared theta d theta. And now I will be really, really nice. Going to look like the integral of u to the power of m times 1 plus u squared to the power of k minus 1. And here, all of this becomes du. So if you want a recipe, then you have that recipe. But more likely, you'll have to just remember the process. Okay. Let's see why in my note I have less steps.
Is it because you're subtracting 1 from k?
Right. Well, subtracting 1 from k, but k is the power of secant squared. So really, that 1 is secant squared. It's secant squared to the power of 1. And I need the secant squared with d theta. Make sense? Let's look at an example here, okay? So here's an example. This would be example 5. We want to evaluate the integral of tangent theta to the 6th power times secant theta to the 4th power. Once again, I can use the recipe. I can say the heck with it. I know what my goal is. And I think not using the recipe here will be easier because, remember, my goal is I want to have secant squared at the end. So I'm going to say that my integral, I, is I'll keep the tangent theta to the 6th power, and then I say secant to the 4th because it's even. Remember, I can do it if I have even powers. I'll write secant to the 4th, secant squared times secant squared. And I'll save a lot of time. Okay, so here it is. This is my du. Okay, the next thing I want to do, I want to replace this secant squared, with 1 plus tangent squared. So one more step, I'll write tangent to the 6th. In here I have 1 plus tangent squared. And here I have the secant squared d theta. And now we let u equal the tangent. And therefore du equals secant squared theta d theta. As you see, I don't even go back and try to fit m and n and k here because it will take me as much time as to redevelop this strategy. And now we're going to say that I, the integral, is really the integral of u to the 6th times 1 plus u squared. This is to the power of 1. And then du with a solution. Well, let's clear the parentheses and get u to the 6th plus u to the 8th du. Right? And the antiderivative is, of course, 1/7 u to the 7th plus 1/9 u to the 9th plus c. And finally, going back to the substitution, this substitution right there, and bring it back the tangent, so it will be 1/7 tangent theta to the 7th power plus 1/9 tangent theta to the 9th power plus c. Again, you can go ahead and take the derivative, and with a little bit of trigonometric identity, manipulation of trigonometric identities, you can recover the integrand by reversing the process. Okay? So what happens if we don't have an even power of the secant?